Hello, my name is Todd Caldwell. I'm a research hydrologist with the U.S. Geological Survey in the Nevada Water Science Center located in Carson City. I'm one of several working on the National Drought Program for the USGS Water Mission Area. And today I'd like to present some background on groundwater drought and drought propagation through the hydrological cycle. Drought metrics, like the Standardized Precipitation Index for rainfall and the Palmer Drought Severity Index for soil moisture, are used to characterize drought severity as the product of its duration and magnitude. These indicators reflect physical drought impacts in various sectors that cannot easily be weighted or aggregated through some sort of direct measure. As such, indices are critical for drought mitigation and operational water management. More holistically, the rate of drought onset and recovery and its propagation through the hydrologic cycle can improve our ability to predict the response of groundwater and stream flow to these climate anomalies. Hydrological drought differs in dynamics from meteorological drought. The large size of most groundwater systems buffers the impact of meteorological drought, which is often delayed and attenuated with timescales ranging from months to years. Onset is the period where a given anomaly or index drops continually below a specified threshold, indicating the start of drought. Recovery is the period of positive anomaly increase, terminating the drought. Each hydrological system may have a different onset and recovery period, as well as different rates of change as drought and onset and recovery propagates through the whole system. The rate and lag of onset and recovery and the propagation from precipitation to groundwater within a given basin can provide information on watershed resiliency and vulnerability. A last note on this figure, while drought events are by definition extreme events, drought occurrence across the entire hydrological system is a relatively common feature, noted by that red line on the bottom. Some components are almost always in drought regardless of the others. Monitoring wells are perhaps the most direct evidence of groundwater drought. However, the time series of levels can be short, sporadic, and incomplete in national groundwater databases such as the National Water Information System and the National Groundwater Monitoring Network. Wells provide a keyhole into the aquifer, but not necessarily a direct observation of aquifer storage or response to drought. Observation wells are not always in shallow, unconfined aquifers directly recharged by precipitation. Wells are more often in areas of significant groundwater withdrawal for irrigation, and drought may likely increase such withdrawals. Models, on the other hand, estimate aquifer storage and are generally constrained by precipitation and stream flow, but many other uncertainties in these models are often lumped into groundwater storage. Remote sensing, primarily through NASA's GRACE satellite, provides a direct measure of total water storage, but requires models to disaggregate these gravity anomalies into changes in groundwater storage, and the spatial resolution is very coarse. Finally, data assimilation blends models and observations from satellite and in situ data to statistically push the models towards observations and reduce model uncertainty and bias. The top right figure shows the correlation between shallow groundwater storage from the GRACE data assimilation product and over 4,000 observation wells with more than 10 years of data. Darker symbols show wells with higher correlation to GRACE, indicating a greater coupling to atmospheric conditions. Note the scatter with the high correlation for a well in Alabama. The blue crosses on the map indicate no significant correlation, such as shown in the lower scatter plot of the Last Chance well in Nevada. Here, groundwater mining is lowering levels independent of drought. While GRACE does measure groundwater withdrawal, data assimilation cannot fully adjust these models for such human-induced changes to the water balance. Monthly maps of terrestrial water storage change are constructed from NASA's Gravity Recovery and Climate Experiment and the GRACE follow-on satellites, which detect small changes in the Earth's gravity field caused by the redistribution of water on and beneath the land surface. The paired satellites travel about 140 miles apart at an altitude of 300 miles and record small changes in the distance separating them as they encounter variations in the Earth's gravity field. The vertical extent is measured in centimeters of equivalent water thickness, which is mostly related to near-surface water storage in vegetation, soils, groundwater, and reservoirs. The terrestrial water storage is generally decomposed by depth into soil moisture and groundwater using land surface models. The spatial resolution is 1 degree or about 400 kilometers, which is too coarse for local or even regional applications. At larger scales, GRACE provides a direct measure of storage anomaly and precipitation needed for recovery. For example, the GRACE data measured a departure of nearly 90 million acre-feet during the 2011 drought of record in Texas. Nearly 150 millimeters of precipitation would be needed to recover from the drought, which didn't occur until 2015. In order to increase the temporal and spatial resolution of GRACE data and to isolate groundwater from total terrestrial water storage, scientists at NASA Goddard Space Flight Center integrated GRACE data with other on-ground and space-based meteorological observations within the catchment land surface model using ensemble Kalman filter or a type of data assimilation. To increase record length and develop more robust percentiles from relatively short GRACE mission, which just began in 2002, a bias-adjusted open-loop climate land surface model was developed using different meteorological forcings to create a full climatology over the 1948 to 2009 simulation period. This GRACE data assimilation product now provides weekly percentiles of shallow groundwater drought at about a 15-kilometer spatial resolution, and it's used in the U.S. Drought Monitor Program. Groundwater data at the appropriate scale remains a big challenge in monitoring drought in the groundwater systems. As drought propagates through the hydrological cycle, there's a significant lag in the onset and recovery of the groundwater system. Furthermore, humans compound drought signals by changing levels through pumping. Ultimately, we want to be able to predict how much rainfall is needed for drought recovery and how quickly we can expect this recovery and which watersheds are most vulnerable. Furthermore, we're interested in how hydrological drought affects the interactions between surface and groundwaters, since most groundwater is recharging surface waters. And what data can we develop to improve prediction of groundwater drought? We need more wells, better spatial representation in models and satellite data, or a better way to implement these models using data assimilation. And with that, I hope we have a good discussion this afternoon. Thanks for your time and attention.